Okay. Welcome everyone to today's webinar on fire design workflows. My name is Marius and I'm a support engineer here at IDEA StatiCa UK. Before we get started, some preliminaries regarding our webinar. You'll notice on your right-hand side the control panel. And since your microphones will be muted, if you have any questions, please enter them in the questions pane and then I'll get round to them. This could be issues with the webinar itself, if there are any problems, or if you have any questions with the material being presented, and then you can take a look from there. The webinar is recorded, so you can watch it after the session's end. And joining me today is Kosti Chazopoulou, the Technical Director here at IDEA StatiCa UK. Can you hear me, Kosti?
Yeah, everything is okay. I can hear you and I can see your screen. Welcome everyone, by the
way. Okay, before we get started, we are going to run a quick poll. Here we go. Should be able to see it now. This is just to gauge how everyone conducts fire design currently. A little bit longer.
Nice.
And once this is done, we will show the results for the curious.
Yeah.
Just about, well, most of you have voted, so I'll close it in a few seconds. And we can take a look.
Yeah, I think we can close it, Marius. I
I'll
believe
close
that
it
most of the
now.
people have voted.
So you should be able to see the results now. From what I can see, most people are not familiar with fire design checks. About a third use tabulated methods and the rest use advanced analysis already.
Yes, the results are really interesting because especially right now that legislation is changing, especially in the UK, I think that fire design checks should become a part of the daily engineer's workflow. So yeah. I think that we should deactivate our cameras.
Yeah.
And I will share my screen to continue with.
Yep.
Okay, Marius, just let me know if you can see my screen.
Yep, I can see the presentation.
Nice. Okay, thank you for the introduction. And as we already seen in the poll, designers are using simple or tabulated methods for fire design. And this is mainly because we're used to applying fire protection in our structures. However, I think that using performance-based fire design may save a lot of resources from a financially and environmental point of view, because fire protection is quite demanding from this aspect. The thing is that until now, performance-based fire design workflows were tedious, and in this webinar we will demonstrate the tools that we have developed to help engineers deal with fire design situations. So before moving on with the webinar, it makes sense to start with a short presentation and introduction into the principles of fire design. Of course, we will do that in the context of Eurocode. And basically, the generic procedures are described in detail in Eurocode 1991, Part 1-2, named Actions on Structures Exposed to Fire. So in this part of the code, two design approaches are identified. The first one is called the prescriptive approach, where we're using nominal fires to generate thermal actions. And there is another design approach that's called performance-based approach. We're using fire safety engineering that refers to thermal actions based on physical and chemical parameters. In IDEA StatiCa, we follow this second approach since we're analyzing parts of the structure. And to perform this kind of analysis according to the code provisions, we have developed tools to accurately determine mechanical actions and boundary conditions of substructures that are then subject to an advanced analysis. When I say substructures in this webinar, I mean either connections or frames or members. In this part of the code, we're also defining the load-bearing requirements of structures during fire exposure, and this is defined as an accidental design situation. And in this situation, the representative action of the variable load is defined in this paragraph. So the structure should be able to resist the calculated loads under this accidental situation for the required fire resistance time, which is usually denoted with a letter R followed by the time in minutes. Another important aspect of the calculation is the selection of the temperature time curve, which is basically the gas temperature of member surfaces as a function of time. In IDEA StatiCa, we use the conventional curves defined in the code. Besides the generic part that was previously shown, which outlines the design procedures, there are specific rules for each material that is covered in the Eurocodes. So, in the context of today's webinar, that we will be discussing steel structures, Eurocode 1993-1-2 applies. So, to perform checks on steel connections and members, we need to apply additional rules that are prescribed in this part. And let's start with the stress-strain curve, since IDEA StatiCa uses a materially nonlinear analysis that employs stress-strain curve, that for elevated temperatures that occur during fire situations, these stress-strain relationships must be modified according to the provisions of this part of the code. And the reason is that we need to accommodate the loss of strength. So in this stress-strain diagram, we can see that after some time, the third branch demonstrates a significant loss of strength after some temperature. Another way to understand this effect is through reduction factors for different properties of the materials. So in this diagram, for example, as temperature increases, there are factors that introduce a significant drop to the corresponding property. The property is either the yield stress or the modulus of elasticity, etc. In the context of IDEA StatiCa, we call these curves degradation curves. For our worked examples, I will be using a simple fictional structure that was created in a global analysis software. And this is basically a steel platform that's supported on two main steel frames. In the global analysis software, the structure was fully designed under ULS and SLS loads, and it was also assessed under the fire design situation. The assessment was performed for a required fire resistance of 30 minutes, and the temperature time curve was the ISO 834 one. Please note that these settings are project specific and depend on the structure and the type of fire scenario. To get started, I have transferred this structure into Checkbot, and Checkbot is the application we use to manage our BIM workflows without disrupting the already established engineering workflows. To do that, we have created a rich collection of BIM links with the most important structural analysis applications, and through these BIM links, information about geometry, connectivity, and loading is collected and managed in one place, which is the application, the Checkbot project file. This is very important because that way we can maintain information about already designed parts and just synchronize the changes that often happen in engineering workflows and just update the calculations without too much effort. In this webinar, I will pick and design a connection with IDEA StatiCa connection and then continue with the checking of a whole frame in IDEA StatiCa member for the fire design situation. For the second case, the frame will include the laterally supporting members, including their connections, to account for the stability issues that may appear. The process will be demonstrated through short, pre-recorded videos to save some time. And without any further delay, let's move into IDEA StatiCa Checkbot and open the project I have already created. Obviously, the whole structure was transferred, and we can see the steel members and also a loading surface. Let's deactivate the member names and also switch the view to transparent to be able to show the cubes that denote the location of the connections. For both the connection and the member frame check, we need to export substructures and create sophisticated sub-models that describe their behavior under the fire situation and also under the ultimate limit state condition. To ensure that these sub-models can replicate the expected behavior, we must recreate the boundary conditions to match the ones of the global analysis. In this application, besides the geometry, we also import loads and can guarantee an accurate representation of the boundary conditions. So let's pick a node, and we can, by picking the node, we can visualize moment diagrams or shear force diagrams for any load case that was imported. Let's move, for example, to the variable load case or any combination. Or we can even display a group of combinations, an envelope, and this is the reason that we now see two diagram values, a minimum and the maximum one at the same time. I will move to the loads dialog to see the imported combinations for both fire design and the ultimate limit state. And these combinations can be grouped in what we call result classes. These result classes should be our envelopes and use different sets of combinations for different structural parts. This saves calculation time when we know the critical combinations, and we can also create custom result classes, as we will see during the export of the frame design. The software can also decide and export only combinations that produce extreme stresses when the evaluate critical effects option is active. Now the cubes in the graphical window denote locations of connections, and empty cubes are not yet designed, while highlighted cubes contain designed connections. I will, for example, pick the highlighted cube at the location of the base plate and see that a preview of the connection and its design status. So let's pick the corner node, and since this is not designed and checked, no preview is available. In its properties, I can see the connected member names that correspond to the global analysis software. I can also see the result class that will be exported for the design. And when everything is set, I'm just pressing the open button that will take me into IDEA StatiCa connection to continue with the process of exporting and designing a connection. So, in IDEA StatiCa connection, we can see the geometry of the node, the incoming members were imported, and what more important, all combinations were imported, and since evaluate critical effects was deactivated, everything was transferred, not only the critical values. And we will start by modeling the connection, and to do so, I will use the connection library. The connection library is a huge collection of templates that match the member topology, and when I press the propose button, I see several options that match this topology. I have already created a template called Fire Design Node. I'm pressing OK, changing the applied port to M24, and the template is applied. Once this is done, the connection is ready to be analyzed, and we will start with a stress-strain materially nonlinear analysis, which will take place for all ULS combinations, excluding the fire design one, named Fire-1. So this combination will be deactivated by just deactivating the checkbox in front of the combination. And another thing that's noteworthy is that since these combinations are imported from a global analysis software, they're in equilibrium. So for example, when I select ULS1, there are no unbalanced forces in the corresponding table. Let's just press the calculate button to solve the connection, and at this point a CBFM sub-model is created. The active load cases are applied in steps using a materially nonlinear analysis. So let's wait a bit for this analysis to complete. In any case, the video moves a bit faster at this point. And when the analysis completes, I can see a short summary of results at the top left window, where we can see really low utilizations. The view we're looking at is called the overall check, which provides a colored view of the connection, and gray color means that under the ultimate limit stage, this configuration remains in the elastic regions. Now, to ensure that the connection can develop the strength predicted by the stress-strain analysis, we also need to perform a buckling analysis, and depending on the critical factors, we will determine if the structure buckles before developing the predicted strength or not. Again, I will go and press the arrow below the calculate button and begin the buckling analysis. And again, I'll wait a bit for the results. So the calculation finished, and at the top left I can see a ridiculously high minimum critical factor, and as this is over 15, we know that there is no problem buckling, and we will move on with the fire check, which is relative to today's webinar. To do that, we need to perform a different type of analysis, and this is the reason that I will create an identical copy of this connection by pressing the copy button. The software takes me to the newly created project item, and I will pick the name of the configuration. In its properties, I will set the analysis type to fire resistance. Then, in the temperature property, I will set its value. To calculate it, we see that we also have the option to set the member temperatures manually as calculated from, say, global analysis software. However, the proposed method gives much more accurate results, and I will go with this one. Next, we need to set the fire design settings that match the project specifications. So I will set the fire resistance class to 30 minutes, then make sure that the standard fire curve of ISO 834 is used. Then we will deactivate any fire protection and check the configuration as such. And lastly, we have some options for the material degradation. We have the Eurocode curves and also ISO and the Canadian code, but of course we will go with the Eurocode ones. And again, that was it. The connection is ready, and we just need to press the calculate button and activate the fire combination which is relevant for the fire design. ULS combinations were deactivated, and pressing the calculate button initiates the calculation. So the calculation is over, and again we can see in the overall check that we have a different picture right now, because we have higher utilizations under fire design, and we also have two failing bolts. However, this is not worrying, because this means that we could potentially use bigger bolt sizes to avoid the use of fire protection. And keep in mind that the cost of increasing the bolt size is nothing compared to using fire protection. Now, besides the overall check, we can also take a look at the plate checks, where critical temperatures for each component is displayed separately. We can also see the magnitude of the yield stress, which is very low following the material degradation curve, and the yield stress reduction due to high temperatures. And at this point, we can also calculate the temperature button and have a graphical view of the temperature of each element in the graphical window. Let's also move to the welds, where the same effect applies. And again, we can see critical temperatures, and we also can see very low resistances. We can also display the code formulas, where we can see the used reduction factors and their application on the equivalent stress. So I'm closing the connection design, which will take us back to checkboard. once this is over. So moving back to checkpoint, we can now see that the corner node is now highlighted, denoting that this connection is designed. And the next step is to design one of the main frames. We will design the one with the highlighted cubes where the connections have already been defined. And this is very important for the accurate definition of the boundary conditions and the assessment of the frame stability due to laterally supporting member. Before we start, let's press the member button and select the members that compose this frame. I'm selecting them graphically holding the control button, and when the selection is over, I will press enter. When this is done, a new entity appears under the members tree item. And to save some time from the analysis, I will now move to the loads dialog. And here I'll create a new result class named RC member. I will pick this, rename it, and make sure that the evaluate critical effects are not active, because I want to pass every combination from this result class into IDEA StatiCa member. And the next step is to drag and drop the combinations in the newly defined result class. So I'm selecting one ULS and one fire design combination. I'm saving this, and then again moving back to members, I will pick the frame I have defined and then make sure that the RC member result class is selected. Once this is done, I need to press the load update button and then just open the open button to take this configuration into IDEA StatiCa member. So let's wait a bit for IDEA StatiCa member to open, and we need to quickly move to the project tab because we want to activate the file design, since this is relevant for our webinar. And returning in the main window, the next step is to go to the settings and do what we did with connection. So moving to the fire design settings, make sure that the fire resistance class is 30, that the fire curve type is the specified one. Then move to the fire protection and make sure that this is deactivated. And lastly, again, we also have some options for the material degradation. We're saving this and moving to the next essential step, which is to determine which combination will be used for the fire design. To do that, I'm selecting the combination named fire-1. I will scroll up in the properties of this combination, and then in the check type, select fire resistance. So now the fire combination is under a separate tree item named fire resistance. Similarly to what we did for connection again, I will add fire exposure and then set the temperature to property to calculate it. And the reason is that we need to use the accurate method for the calculation. Of course, we have the option to set the value calculated in our global analysis software, but we need to demonstrate the accurate method. And that's it. I just need to press the calculate button and wait a bit for the material in nonlinear analysis to complete. This is similar to what happens in IDEA StatiCa connection, and at this point a CBFM model is automatically built and the analysis applies the defined load cases in steps. Okay, so the analysis is over and the graphical window switches automatically to the strain check view, where we can see at the short summary at the top left that everything passes the checks. We can also move to the check and display the yield stresses, the von Mises stresses. The von Mises stresses are low, very low, and this is due to the fact that they follow the material degradation. We can also see in the table of results the critical temperatures, and next to the critical temperature the von Mises stresses are very low. And in line with what we did to connections, we now need to perform a buckling analysis to verify that the predicted behavior here can be developed safely without buckling of the plates. This is an essential part of the CPFM methodology, and we just need to press the LBA button and calculate, and the buckling analysis initiates. Again, we just need to wait a bit for the solver to finish. And again, when the solver is over, we get a really high critical factor that verifies the findings of the material nonlinear analysis. So basically, the frame passes the checks, and we can just close IDEA StatiCa member and move back into checkbot, where once again, when this is back, we can now see a preview of the designed frame and its status below, with a short summary of the design results. And basically that was it. We just checked a frame and proved that for the project specifications, this frame can resist, can maintain its bearing resistance for 30 minutes under in the fire design situation for 30 minutes. And we also designed the connection that where the only problem were the two bolts that we can replace and avoid using fire protection in this case. With this, I'm closing the presentation in this webinar, and the key takeaways is that we have the checkbot solution where we can easily transfer and preserve and transfer accurate substructures that were imported under equilibrium from any global analysis software, or at least most important structural analysis softwares. The fire design workflow can be streamlined even for demanding structures, and we can even apply advanced types of analysis like GM&IA. And lastly, these demanding types of analysis can be performed intuitively, giving graphical results that are easily interpretable at any step of the calculation. And closing this webinar, we would like to initiate a quick poll and just to see if you see any benefit in using advanced fire design methods. So we'll keep this open in a bit, and then when this is over, I will pass the presenter to Marius to close this webinar. I will keep it on a bit because I see that people are still voting and we're really interested to know your opinion on that. So I think we can close the poll and share the results with you. So we can see that 61% of the attendees will adopt the methodologies. People see benefit, but they have their reservations, which is understood because in structural engineering we're a conservative industry, but I think that for the people who have reservations, they can contact us and we can discuss anything about the underlying methodologies and that. So I will pass the presenter to Marius.
Sounds good.
I will hide the poll. I'm not sure, Marius, if you would like to comment on the poll.
Yeah, I think like you said, as fire design becomes more of a requirement, potentially there will be more take up. But yeah, if there are any reservations, and you have any additional questions that you'd like to address that might be because of these reservations, then feel free to let us know, and then we can try and help with that. Do we have time to look at some of the questions that have been brought up? Steve?
Yes, I'm looking at some questions. So can you please repeat that, Marius?
Yeah, no, if we have time to look at some of the questions, there are some that were brought up that I haven't covered from within the go to answer panel that we could. So, for example, for those interested, the BIM links, today one of the BIM links was presented, but you can use, one of our users asked if they can use robot. There's a list of BIM links that you can connect to. Robot structural analysis is one of them. Let's see. There's a question about a few about protection and applying fire protection to some of the faces instead of all of them.
Yeah, basically, there are many options. You have the option to apply protection in some of the faces of the members. Yes, it's feasible.
Mm-hmm. Let's see. The question about the temperature of the bolts and welding and the reduction factors, that relates to the nearby plate temperatures.
Yeah.
So reductions, so the temperature of components will be based on the plate temperatures.
Yeah, I think that it would make sense to answer this through email, where we will send a link to our support center where these are presented in detail, in more detail.
Yeah, I think some of these questions will be, it might be good to add some resources as well, or if it expands some more technical, if there are some resources related to the question, it might be helpful to answer those using screenshots essentially as well. So usually that helps. Okay. So think that covers it for now.
Okay, so yeah, I think we can close this webinar, and in
Hmm.
case there are remaining questions, you can just drop a line to us through our emails, and we will be happy to answer any question you may have.
Yep. I'll be taking a look at any unanswered questions that were raised during the webinar, and we can discuss them separately as well. So you can get those answered, as Ghostly said, via email or our support channel.
Okay,
So I think that's it for this webinar. Thank you for joining us today.
thank you for attending, everyone.